So I'm a professor of mechanical engineering with courtesy appointments in machine learning, biomedical and robotics. And I'm also affiliated with CMU's CyLab Security and Privacy Institute. And the focus of my talk today is a project that's been ongoing for a few years now. It's the VideoVitals, is what we're describing it. And it's non-contact estimation of vital signs using a mix of AI methods and also kind of first principles approaches. I would like to acknowledge the broader team at CMU, my colleague, Professor Laszlo Jenny, and our excellent, hardworking grad students who, if they were not part of this project, not much would get done. So all the glory and credit goes to them. And also our funders, the Bill and Melinda Gates Foundation, for funding this work. So the vision really is motivated by the kind of end user and communities that we're trying to reach, and primarily this work has been motivated by individuals in resource constrained environments. So there's been this kind of emergence of mobile devices in communities. And really, as a researcher, I've always been interested in not only the foundational, fundamental science, but also um, exploring how work that we start in the lab can actually have impact in the real world. And so typically what we see in the digital health space is really this mismatch of the researchers that create the technologies and then the individuals that consume them. And some of the assumptions that we may have in the lab is that everyone has internet. There's demographic similarity between the study population and the test population, and just the generalizability of our algorithms. And I'll provide some examples of real world cases where, many of these assumptions do not hold. And as a matter of fact, some of these assumptions is what we um, use to constrain how we developed these algorithms. So we assumed the opposite, that there was not internet connectivity. And the question is then, what can you create that is deployable on the edge that doesn't require internet? So the goal is to develop and deploy non-contact based methods. Primarily, this is focusing on just using a mobile device, primarily the video camera modality, and developing both theoretical, interpretable driven approaches and also empirical, what is typically called black box driven approaches to estimate these vital signs that are used in the field. So a survey of the literature really focuses on, if you took a distribution of where is the active area of research, it's really in pulse, heart rate estimation using these kind of non-contact based approaches. What our group has specifically focused on are contributions across the different vital signs spectrums, with our most recent work being blood pressure and blood glucose estimation. And again, the emphasis here is that we want to constrain on a mobile device or on a phone or video, and make these approximations using the single modality. So if we summarize what differentiates our work from others in the field, we not only want to demonstrate these algorithms in the lab, but we want to be able to deploy them in real world conditions and across diverse demographic data sets. And we want to have a comparison with FDA approved kind of ground truth devices. So I know that this is a clinical community, so I'm not going to kind of spend too much time on what the importance of vital signs are. And I'll jump straight into how we actually accomplish this. So the principle is based on video pixel magnification. You can see the video on the left here is a video of an individual. If you magnify the video on the right, you can see very small changes in the color intensities of the pixel. And this corresponds to when blood is flowing through different regions of the body. And the great thing about these techniques is that they are agnostic of the demographic variability, because really what you're looking for is a change. You're looking for a change in pixel value. So some of these you can see them more apparent than others. And so what you end up getting, which is here on the right, is time series data that maps the intensities of pixels over time. And using signal processing techniques, you can then map this time domain into a frequency domain and extract or estimate the signal, which in this case would be a pulse rate or respiration, etc. So this is the algorithm that is developed in real time. So you can see here that it takes a running average of frames and estimates or calculates the peak of these signals. And with that, you can see how many peaks you get in a particular interval, and that's what's used to approximate the pulse rate. So this work was also connected to an NSF-IU CRC that I used to direct at my former institution, that then led to this kind of global deployment. So with the ability to extract signals with just video, our more recent work in this kind of space is trying to see if we can take two different readings on an individual. So this is the face and the hand, and make approximations about the blood pressure, and this is based on the velocity of the blood at two different regions of a human body. And so right now we're trying to experimentally validate this. This is collected in the field. You can see the ground truth FDA approved traditional arm cuff blood pressure reading, and we're trying to make an approximation of this blood pressure reading just based on a non-contact video. So instead of applying pressure and slowly removing it, we're trying to measure the velocity of blood at two different regions. So based on this, we want to then combine these two signals to approximate the systolic and diastolic readings. So we collected 2,000 samples from 2,000 participants across the world, and we hopefully will be publishing or working on this and having this go through peer review shortly. So up until now, I've shown two vital sign estimation approaches: the ability to estimate pulse rate, the ability to take these RPPG or pulse rate signals at two different locations in the human body, and then with that make an approximation of blood pressure. And our also recent work that was just published in IEEE Transactions is the ability to, again, with vision, estimate or classify whether or not an individual has an elevated temperature. And this is without a thermal or infrared camera. So if we look at the kind of the principles of light and how they interact with different surfaces, what we're trying to observe is, can we measure can we determine how much emissivity is communicated by the skin. So this is skin temperature, not core body temperature. But with that skin temperature, determine if someone has an elevated temperature. So the way that light specifically interacts with the human body, we have these different, so we have specular, scattering, absorption. And again, these are related to this figure that shows the interaction with light. What we wanted to do first is to determine with just RGB, can you just look at the differences in reflectance? So when light bounces off of a human skin and it's observed by a camera, would this be enough to determine skin elevation? And so again, anyone in the optics knows that this is not possible because we're not using a thermal camera. That's the whole point. So this hypothesis is rejected because we cannot just use this reflectance to estimate temperature. However, there's an interesting phenomena when it comes to measurement devices. And so this is one of those situations where the measurement device itself, due to the error that they possess when observing a system, can be exploited in ways that give us an approximation of core temperature. And by that I mean, if you have an individual who is being observed, and this is true for both thermal cameras and RGB cameras, the core temperature of the body, obviously in a short period of time, doesn't change. However, the angle in which they are being observed, so this is the individual looking straight at the camera and the individual slightly angled. There is a slight difference in the temperature, you can see, of 96 degrees Fahrenheit and 94 just by the change in the angle. Now, of course, we know that the core body temperature itself may not have changed, but the way that the sensing devices capture this data is what has changed. So what we're trying to do is exploit this characteristic by looking at the difference in temperature between these two locations when someone's turning their head. So T1 is one measurement of the reading, T2 is another measurement, and use this to approximate whether or not there exists a difference in this ratio between individuals that have elevated temperature and individuals that have a normal temperature. So this is an empirically derived from this other work of the relationship between the angular emissivity of skin and temperature and angle. So we're using this study to determine how much of a difference there exists in individuals that have elevated temperature and individuals that don't, based on how they rotate their head. So this is a binary classifier, but what it allows us to do is have a margin that separates the change in this ratio of when someone moves their head, and there exists a difference when a population has elevated temperature or sample compared to a sample of participants who have a baseline normal temperature. And so elevated and normal, this is based on the clinical readings of this. So again, going back to our motivation of not only theoretically providing these explanations, but also being able to empirically test these out in the wild, in real world conditions. So this is the experimental setup to actually collect the data in the lab. So you have different locations that we instruct participants to move their head. This was quite an interesting IRB because when we started scratching our head, how do we get participants to have an induced temperature without a pathogen, right? It would have been a nightmare to make people sick just to observe. So we came up with an innovative idea of just inducing the temperature based on heat lamps. So this A here is the heat lamp that induces this, that increases the skin temperature of the participant. The participant then turns their head. We get the ratio of the temperature observed at two different locations. So that's what that ratio is. And we're then able to test, populate data of elevated skin and not, and also in the wild. So the ground truth for this, it were actually um, individuals on, let's say, social media or YouTube that have, uh, let's say, a thermometer in hand and say, I just got this reading. I have an elevated temperature. So that's how we acquired ground truth when it came to real world populations. And again, the goal here is to only find videos where the individual is turning their head as a condition, and then we're able to see how well this model performs as a binary classifier for um, predicting elevated temperature versus not. So here's a confusion matrix and the F score for that. Um, so finally, we also want to not only have these as papers, but really deploy them in the field. So we have a team that is assisting us with developing Android apps, where we have, for example, so this is an FDA approved ground truth device. This Masimo pulse oximeter. We have our system, and again, we're able to have this deployed on mobile devices. So we do have this this app. We haven't kind of put it on the App Store yet because we're still working on integrating with other health systems. This is the app in India where we tested it out on a mobile device. We deliberately constrained the devices to kind of like very low cost average specification. So the specifications on this phone, I don't even think most phones don't have gone way beyond this. The ground truth here is a finger pulse oximeter, and then we're able to determine how much agreement there is between the ground truth and the algorithms. This is in Sierra Leone, where we replicated the results, looking at different demographics and different conditions. And then we also collected demographic data to determine how much does the environment or demographic impact people. And I think this, when researchers make the case for why do we need uh, heterogeneity or diversity in samples, this is a clear example of a computer vision approach of what this happened. So this is me. If you don't, I was actually going into villages to really deploy in communities and say, well, how would this work in a dark room or at the last mile? And when we look at the algorithms themselves, this is an example of a computer vision face detector with a 1% detection accuracy and a computer vision face detector with a greater than 50% accuracy. Why is this important? Because before you can employ our algorithms, you have to be able to detect someone's face. So if you can't detect someone's face, then you can't then apply these algorithms to extract these signals. And so when we start looking at, well, what are some of the challenges in why this algorithm is unable to capture, you can see that, I mean, from person, like as humans, we know that this is a face, right? But if you have an algorithm that like there's a lot of shadowing here, and which makes it quite difficult to. So this is one of my collaborators, Professor Jenny. So this is their algorithm that not only creates a mesh of the face, but also has demographic variability in its implementation. So by having a 3D estimate of a 2D screen, you're able to have way more robust measurements of detecting a face. And so these are examples of the same data set and the two different algorithms and what the percentage of times that a person was identified in all of the different samples. So we published this paper here at the bottom here that in NPJ Digital Medicine, and it's just evaluating these biases in these RPPG methods and seeing how susceptible different algorithms are to them. This is just an example of the total number of frames that are missed by the first algorithm, and you can see for certain individuals. So the blue represents the total number of frames in the video, and then the orange represents how many times that person was recognized out of all those frames. And you can see some of them are extremely poor performing. And again, same thing for the Z face, but in this case, it does slightly better than for some of these patients. So this clearly motivates the need to have these AI algorithms be more robust when it comes to identifying diverse people. And so when you delve into the algorithms themselves, these studies here show some of the data sets that have been used to train these algorithms. I think some of you have seen some of these reports of these face recognition algorithms and maybe misidentifying people. You can think of these in the same kind of class of challenges of having data sets that are diverse to train on so that they could be applied to populations that are of interest. So this motivated us to go on this large scale data collection. So we have collected over 2,000 data sets of faces and ground truth data from participants across the world. And that data, we're currently working with the CMU repository to make this globally accessible so that researchers can benchmark their algorithms based on the diversity of the data sets. So when we looked at these, we wanted to make sure that the differences we were observing weren't due to kind of these external factors. And so we kind of went through a series of hypotheses tests to just determine what are the differences. Are there differences in the temperature that may have been causing differences in vital sign reading? Is it a difference in the populations? So when we look at the heart rate, average heart rate of India and Sierra Leone, we performed hypotheses tests to see, are there differences even in the pulse rate? And based on these ground truth devices and these ground truth readings, then we can then determine how many of these algorithms are in agreement with the ground truth. So same kind of thing. We looked at the differences in pulse rate with female subjects to see if there's a difference in male subjects. And then finally, are there differences in skin tone? So this is a summary of the actual pixel values, which represent the skin tone between the population in India and then the population in Sierra Leone. Now, obviously, visually, we can see that there are differences, but we wanted to get statistical validity to see, does there exist these huge differences? And these are all factors that we want to provide to the community so that they are informed to almost like moving to conditional models of estimation. So these are just examples of, now that we have this baseline ground truth, which is this green Massimo prediction, we're looking at how well our vital signs algorithm predicts or estimates pulse rate for different participants. So finally, I just want to summarize that the reason why this is important, we have the ground truth. What we did was compare these different algorithms that exist for pulse rate estimation, and we wanted to see how many of them had a comparable conclusion relative to this ground truth, which is this Massimo at the bottom here. So in essence, is there a difference in the pulse rate between Indian and Sierra Leone population, and how many of the algorithms would provide the same statistical support for that hypothesis? So I want to summarize by saying, we've been grateful in our lab to not only work on the kind of foundational, fundamental research side, but also going into the field and ensuring that our algorithms that are developed in the lab actually can be deployed in real world environments. We're now scaling up our work. I'm not sure how many of you knew that CMU has a campus in Africa. It's in Rwanda. I'm actually going to be spending a semester there starting in June, just to expand the work that we've done in the Pittsburgh campus. And so we also have collaborators in India and are trying to really make this a global digital health network. So I'd like to conclude by acknowledging our partners in country that have been instrumental in our data collection efforts and our recruiting of participants. And of course, I end with saying that this is a team effort, and acknowledge the hardworking team at Pittsburgh. So with that, I'd like to conclude and thank you very much for your time and for inviting me, and open it up for any questions or comments that you may have. Thank you.
Conrad, thank you very much. Susan.
So Conrad, that was a great talk. I really appreciate it. So the thing I saw, I'm going to think like a behavioral scientist momentarily. And the thing that comes to mind is, even relatively simple measurements, just a regular person, they often need support. Like, for example, a healthcare worker, to try and help them get themselves positioned in front of the camera appropriately, or in the right kind of, in the right kind of shady area. All of these kinds. And I just wonder, in your mind, like, if you think about using this, say, in a trial, say, for example, here's a trial that's always been of interest to me. These are healthcare workers. They work with women who are pregnant, and you can imagine, and they visit them in their villages. This is in Indonesia, and they want to collect a variety of different measurements. And so, how are you thinking about this? What kind of support is required for the actual individuals, regular people, to be able to use this?
Right. So I think that's at the core of the kind of the user interface. And I'm trying to go back to our app. Okay. So the familiarity of the recording device. And so this is we've intentionally constrained this to mobile devices.
Uh-huh.
Um, we are making some assumptions that an individual knows how to use, let's say, a smartphone and knows how to, let's say, click on an app like this. The system launches and, you know, is quite agnostic. I mean, it's quite robust to, let's say, head movements. That was actually one of our first papers, just to reduce the amount of times that an individual's face would not be tracked.
Mhm.
And what we're thinking from a like a large scale deployment beyond just a research, it could even be when someone's watching a movie or just some clip on their phone, and on the back end, the vital signs are being
I see.
extracted. Now, of course, this would be consenting from
Yeah.
the individual, but it could be as they are, let's say, watching a health education
Mhm.
video,
Yeah.
this information is being captured.
Yeah. Yeah. And so would it potentially, though, provide feedback to the person? Like, because I could imagine someone going out into the bright sun or rain, all kinds of things could happen. I mean, because these are just regular people, right? They're not. So would the app say, for example, notice that that the measurements that are coming in are not that of high quality, and make suggestions to the person to try and help them? Does that make sense, or would that be
It does.
something? Yeah.
So those are possible. The kind of adaptive recommendation that is currently not part of the deployment as of yet.
Uh-huh.
However, one way that could be possible is that in addition to the camera, most modern day smartphones have these light sensors. So that's
Yeah.
how the phone knows when you put
Yeah.
your phone close to your cheek, it turns off. Leveraging that light sensor to capture, to determine what is the threshold that this would, the algorithms wouldn't be well performing.
Yeah.
Uh, but again, it still has to be done in the way that that information is communicated back to the user. We're very excited about these uh, generative models that are able to communicate and actually
Yeah.
speak,
Yeah.
because what does RP BPM mean to someone who isn't a medical person, right?
Yeah.
I think if we move away from text and are able to communicate in someone's native language, I
Mhm.
think that's really where the ultimate goal is, where we can kind of link this with some type of voice generative model.
Yeah. Yeah. Cool. That's totally cool. Thanks.
Conrad, very, very fascinating. I'm very impressed that you are such a translational engineer, doing stuff that people like me who are clinical investigators, in populations that are very hard actually in resource constrained environments. So I compliment you on that. Two questions. One is your use of a pulse oximeter. As you point out, it's been kind of, the algorithms were trained on the majority population here. And now you're actually using them in these resource constrained environments. We know that these pulse oximeters are very fallible. There are issues like nail polish, dirty fingernails, motion artifacts, and skin pigmentation. And so how do you kind of normalize? How did you adjust? And then I'll ask my second question.
Yes, so that is something. Let me go back to the actual experimental setup. That's something that we have to acknowledge, that there's an error in the ground truth device itself. And there are more and more studies that are coming out now that are highlighting the scale in which those errors are. I think for this first study, we wanted to just get agreement with the reading of which we're calling the gold standard for now, and then work on how do we refine our prediction models. I mean, ultimately, you want to even these pulse oximeters they're trained on the what are the desks these these actual medical devices, right? And so I think to your point, there exists measurement error in the ground truth, but for now, we've just focused on our algorithms being at least in agreement with those field ground truth devices.
Terrific. My follow-up question actually has to do with this very interesting way of looking at elevated skin temperature.
Mm-hmm.
Now, from my clinician background, if I put on my hat, the skin temperature varies depending upon blood flow. For example, the front of my face would be warmer than my ear because of different blood flows. Then there are issues like subcutaneous fat, my activity levels, like I'm rushing to the appointment. And then there is also the ambient temperature. Sierra Leone and India may be closer in temperature, but still the ambient temperatures change in the room. So how are you adjusting and normalizing or tackling that?
Yes. So I wish I had more time to go into the actual equations themselves, but we are looking at it's primarily the reflectance of light, where again, this is not a infrared camera that we're using, it's an RGB. And what we're doing is looking at the correlation between this established study and what we're able to extract from this angular reflectance ratio. So when it comes to things like let's say the humidity of the air or the differences in the ambient temperature, those are not being considered in the model because we're looking at the ratio of the temperature. And of course, this is exactly why we're not claiming to predict absolute temperature. This is just a binary classifier for now. So even in that binary classification, there is error in the actual numeric value. But what we wanted to do is have a quantifiable way of saying this person's temperature is clinically defined as elevated compared to not. And we're thinking of these as like triage systems, not necessarily to have like as clinical grade where it is the decision made. It's a system in which decisions are made, but it's the system that then triages people for further follow-up.
Fascinating. Thank you. There are others on Mustafa, Simone, all from our mHealth community.
And Vivek, while we're waiting for, these are some of the opportunities that we're looking to expand our collaborators. I mean, you're right. We're engineers and we have more of the engineering lens, and we're trying to expand our collaborations to include physicians and researchers from the medical community, so that some of our assumptions about, let's say, the variability in temperature based on the location that you're measuring that, how much should that be taken into consideration, and what effect does that have in the overall classification of someone having elevated temperature or not, for example?
Interesting. I tease my colleagues. I have a joint appointment in biomedical engineering at UCLA. I tease my colleagues saying engineers come from a solution-rich environment. They're used to forming, they may not always understand the question, the context. And
Yes.
so to me, it's very impressive that you have stepped out of your comfort zone to engage with clinicians. It's very chaotic, and it's driven by a lot of often anecdote. So I compliment you on that. Well, we have Mustafa here. Mustafa, go ahead.
Yeah. So great presentation, Dr. Tucker. I'm not even close in terms of the technical knowledge behind this research, but in terms of applications, I wonder whether your findings create a foundation in the future to identify like looking at the group of people at the time and identify some of these vital signs, like the looking at the street, like this type of applications can have some value given the the example of pandemic conditions, etc. So do you see that in the future you will be able to put this type of applications like in the public domain and look at instead of individuals but a group of people?
So thank you very much for that question. I think there's an opportunity to definitely map this to population health, where you could start maybe even looking at the pattern of a disease vector. I think the ability to be able to do this on a mobile device without any additional peripheral attachment is absolutely critical in enabling the large scale populations to quickly make these approximations. Now, the potential use cases, I think there are a wide range of use cases that could be that could be deployed. To Susan's point earlier, the user interface and the user experience is absolutely critical in getting adoption. I think if the deployment on a device isn't intuitive, then the algorithms themselves may be readily available, but the frequency of use may not be desirable. So I think there are lots of opportunities for us to think through about how would this be deployed at scale.
So you work with the Gates Foundation, and these population-based studies in resource-constrained environments are tricky. Does the Gates Foundation provide you some kind of infrastructure or resources beyond, the funding to enable you? Because I don't know too much about what kind of infrastructures they have for these kind of research.
Right. So that's been a challenge because, this area of research is also, my understanding, new to them, where, they're funding research for innovative solutions that could be deployed in resource constrained environments. So it's almost like we're both a funder and the researchers are learning about all the challenges and complexities as the project moves on. You're absolutely right. There's more to the complexity of this beyond just the algorithms themselves. And, I think this is why it needs to be even beyond just a single funder where, we're engaging with, hospitals and community workers who could potentially expand the breadth of what we're trying to do.
Interesting. You do know that the WHO has now issued white papers emphasizing digital health and self-care. And so I don't have them handy, but I remember them emphasizing mobile devices as one way of getting population level global health. So you're onto something.
That's great. And it's my understanding that, WHO or NIH, to be competitive, it's not just the engineering solution, but also working with medical decision makers or researchers. So we would love to partner with more researchers and decision makers from the medical community to go after some of these grant opportunities. And I think that's the next phase that we're very interested in pursuing.
Perfect. For all the people who will be watching your talk asynchronously, they know how to reach you.
Yes, please. We would love to collaborate with you on a proposal.
Great.